Okay, so our lesson today is on continuous functions. And we made it pretty simple when we were in pre-cal. We just said, well, if a function is continuous, then when I'm drawing it, I don't have to pick up my pencil. Um, we talked about gaps, we talked about holes, we talked about asymptotes for reasons for discontinuity, but we didn't really give it a formal definition. And so the formal definition involves limits, and we didn't know a whole lot about limits at the time. So now maybe our formal definition will make a little more sense. There are three things that have to happen for a function to be continuous. First of all, there has to be a value of that function. There has to be a function value that exists at c. Secondly, the limit as x approaches that value of c exists. And then thirdly, the limit and the value have to be the same thing. They have to be equal to each other. So let's look at what that would look like in a graph or in a picture, and I think it'll become more clear. These are all reasons for discontinuity, things that are not continuous. So obviously this one's got a hole in it, right? A hole or even an asymptote at c would mean that there is no value, that f of c is not defined. So this one doesn't pass condition number 1. So not continuous. So in this second picture, the first condition is true. There is a value at c. F of c does exist. However, condition 2 says that there has to be a limit there as well. And we already know that the limit from the left exists, the limit from the right exists, but the overall limit here is not existent because they are not approaching the same thing. So doesn't pass condition 2. So this would be like a gap between them. This last example also has a value at c. F of c does exist. And the limit at c exists. The limit at c would be whatever the y value is here. So we do have a value. We also have a limit. But condition 3 says that if it's continuous, the limit and the value are the same. So the limit and the value are not the same here. This does not pass condition 3. So obviously all three of these are discontinuous. We know that even just from the basic definition that it's got a hole. We'd have to pick up our pencil to draw any of these graphs. But formally, they have to pass all of these conditions. All right, so this next section we're going to look at some equations and see if we can determine if these functions might be discontinuous or not continuous. So things that would cause them to be not continuous would be things like holes or maybe gaps in the graph or even asymptotes. Those are things that we know would make it impossible to graph them without picking up our pencil. So all of those are places where the function would not be continuous. But we're going to talk about those in terms of the three things that have to happen in order for continuity to exist. So in this first one, we're going to go ahead and factor out the denominator. And so let's use some of our information from pre-cal to figure out what's going on here. I know that these cross out and it would reduce to 1 over x plus 3. And so since they cross out, I know that there's going to be a hole in this graph. There is a hole in the graph where x equals 3. I also know that there's going to be an asymptote in the graph where x equals negative 3. So I know that at both of those places, this graph is not continuous. But if I wanted to describe that using the concepts that we talked about on the other side of this paper, then I would do things like this. For the whole, I want to first go with, the first condition was that the value at that place had to exist. Well, at a whole, I've got an open circle, and there is no value. Or if I plug 3 in here, I get 0 over 0. So there is no value here. The value does not exist. And because the first condition is not met, then I could say this, therefore, these 3 dots mean therefore, this function is discontinuous at x equals 3. All right, same thing for our asymptote. Go with the first condition. If I were to plug in -3, there's an asymptote. I plug in -3, I square it, I'm going to get, what would that be? -6 over 0. Also not defined. Therefore, f of x is discontinuous at x equals -3. Now, we could also have gone on to condition 2. In condition 2, the limit is not going to exist at -3. However, the limit would exist at 3. The limit as x approaches 3 of this function, I could find by plugging in 3 here, I get 1/6. So the limit does exist, but since the value doesn't, we know it's discontinuous. I'm sorry you couldn't see that. The limit as x approaches 3 of the function is 1 over 6. But since there's no value, it's not continuous. Alright, let's see if I can focus this a little more. Maybe not. Alright, so on this next one, we need to talk about what this graph is kind of going to look like, because otherwise I don't think we'll understand the continuity portion. So remember, the absolute value can be positive or negative. So this is actually, it could be x minus 3 over x minus 3, or it could be the negative of x minus 3 over x minus 3, because the absolute value means positive or negative. Well, this is equivalent to 1. This is equivalent to -1. Now, so when I graph this thing, I know that at 3, I can't really define this function. The denominator can't equal 3. So when x is 3, I'm going to have a problem. But I do know that on the negative side of this, everything I get is going to always give me -1. If I put 0 in here, 0 over would give me -3 over -3. Sorry, I was pointing to the wrong graph. If I put 0 in here, I'm looking at the negative side of this graph, I would get -3 over -3, which is 1, and then I need to make that negative, so I get -1. If I were to put something to the right of 3, that's the positive side of 3, then I would put something like 4. I get 1 over 1, which is +1. So everything on this side of my graph is going to give me +1. This graph is kind of an important one to know. We're going to talk about how to split that up when we talk about derivatives as well. But it is kind of one that you kind of need to know, and we're probably not super familiar with. But I know that at 3, it is not defined because it can't divide by 0. So when we're looking at, which of these rules to use, I could just say that rule number 1, f of 3, it doesn't exist. So therefore, this graph is discontinuous. At x equals 3. Okay, so let's take a look at these piecewise functions. Okay, so let's take a look at the graph of this function. We know that this equation is a line, and it goes through the origin. Slope is down 2, so I'm going to go down -2 over 1, down 2, -4 over 1. So we get this line right here, and it says that we're going to use that line for x is less than or equal to 2. So it is equal to 2 there, and we're going to use this as that left side of the graph, the left-hand side, less than 2. All right, this other function is a parabola. Just so we can save a little time, I went ahead and put it in the calculator. Here's our graph. And so we want to know what's going on at 2. And at 2, we're down 1, 2, 3. So 2, -3 is where this graph would begin, because we're supposed to start it at 2. So right in here is where this graph starts, and then it curves up. All right, so obviously at 2 we have a problem. So let's talk about what's going on here as far as the 3 things that have to be fulfilled. First of all, at 2, is there a value at f of 2? Well, the answer here would be yes, there is. When I plug 2 in, I'm supposed to use this function, because that's where it equals to when x is 2. So I would get -4. So this does have a function value. All right. Now the second portion says that I want to be able to find the limit as x approaches that value. And the limit as x approaches 2 coming from the left is -4, coming from the right is -3, so therefore our limit doesn't exist. And since the limit doesn't exist, therefore f of x is discontinuous at x equals 2. All right, on this last function in this section, let's also look at this graph. We know that this piecewise function has a line for the left of 2, and so this line starts at 2, and our slope is -1, so down 1, right 1, down 1, right 1. Oops, and I probably shouldn't have filled that in because it doesn't say it's equal to, so let me fix that real quick. So we'd have a little open circle there. And this graph is the left. And then we have our square root function graph, which is shifted left 2. And I really think I meant to make that x -2. So we're going to change this because I want to show you one that kind of does work out. So this graph, if we change that to a -2, would be shifted to the right 2. And so now that square root function graph would fill this in, and we know the square root function graph goes this way. And so let's go through our rules. If there's a problem, it would be at 2, and f of 2 does exist. F of 2 in both of these, whether you're coming from the left or the right, is 0. Then we're supposed to talk about the limit as x approaches 2 of this function. Well, whether we're coming from the left or the right, the limit is 0. And since the function value and the limit are the same, since f of 2 equals the limit as x approaches 2 of the function, then we've checked off all 3 boxes. Therefore, this function is continuous. All right, so this last little piece of information is talking about functions being closed on an interval, continuous on a closed interval. And so this is kind of important when we start talking about derivatives later on. And we've already discussed a little bit about functions similar to this. But we know that this, well, maybe we know, this is the graph of a semicircle function with a radius of 2. So graph 2 units in all directions. It's a semicircle function graph. And this function is continuous. I don't have to pick up my pencil to draw it. However, it does stop. I don't have values on either side of -2 and 2. And so this function is continuous over the interval from -2 to 2, or in the domain from -2 to 2. So continuity can be described within just the closed interval. If I were talking about is this function continuous for all real numbers, my answer would have to be no, because the graph stops between -2 and 2. Oh, sorry, you can see what I wrote. There we go.